All right, so having said that, let's go into the baseline predictor. This is the step number 1 before we can afford to go to step number 2 on neighborhood predictor. So baseline predictor does not utilize the global structures of the users and movies rating. We're going to start the baseline with the baseline of the baseline. That's the laziest predictor you can think of, the average predictor. Let's call that R bar. R bar is simply the summation of all the RUIs across all the UI pairs where there is a rating, and then divided by the total number of such ratings. That's it. It's simply the average. It turns out that in the Netflix price training data, 100 million data points, R hat is 3.6. That is, over all these 100 million ratings, the average is 3.6. And we can say, well, that is our prediction. We predict that all the users and movies interaction will be 3.6 stars in the future. Clearly, this is very lazy. We can do a lot better than this. For example, we know that certain movies are better and certain reviewers are harsher. So let's say the predictor, R hat, is R bar, but with some bias terms. So B, bias terms with regard to the user, and bias term with regard to the movie. So our R hat UI is the average predictor, the laziest one, plus some bias term on that user, and some bias term on that movie. And now we can look at the root mean squared error. We can also take the square root of this root. So we'll just look at the mean square error, because that doesn't change our answer of the optimal parameters. So we look at the summation of the difference squared, difference between our UI and R hat UI squared. We can also delete the step of dividing by the total number of ratings, because that's just a constant that doesn't change our answers. So this is our objective function for the minimization. Minimize over the set of BUs and BIs the summation of the square of the differences between the ground truth RUI, which you have in the training phase, and the prediction R hat UI, where R hat UI assumes this formula. Okay, so this is the function involving some squares of the BU and BI terms. R hat is not your variable because it is just the average, say 3.6 for Netflix, and the BU, BI are your variables. That's an optimization problem. You've got an objective function, which is a square, therefore not a linear programming anymore, but we'll see this is a nice nonlinear programming. And there's no constraints. Okay? The variables are the BU, BIs, and the given constants are the known truth RUIs, and this simple scalar R bar. That describes the baseline predictor training optimization. So let's take a look at a particular example of this. Maybe get rid of the R because we are effectively taking the square root of the error, the mean square error minimization, or the total squared error, since we're not dividing by the number of ratings either. Let's say we have just 2 movies, A, B, and we just have one user, 1. So this is a ridiculously small example. In fact, it's so small that we have more parameters than we have data points. We have 3 parameters, BA and BB for the bias terms of the 2 movies, and the B1, which is bias term of this single user here. We have 3 parameters, and we have 2 known ratings from the ground truth, R1A and R1B. And what is our minimization problem? It is looking at the square of the difference between the prediction and the ground truth. Since we're taking the square, it doesn't matter which way we write out the difference. Let's say we write out R hat minus R. That is B1 plus BA plus R bar. Okay, this is our prediction. R hat of 1A minus the actual 1A. This thing squared plus the other error, which is 1a b1 plus b plus the average r bar minus the actual 1b rating squared. So this is the r1b hat minus r1b. This is the r1a hat minus the actual r1a. Okay, we take the sum of the squares of the differences, and that is the objective function. We want to minimize this objective function subject to no constraints over the three optimization variables, namely our three model parameters b(a), bb, b1. So our question is this an easy optimization or not? It's clearly not linear, but it is an unconstrained quadratic minimization over the variables. It turns out it is a very easy problem. It is so-called least squares.